Hi guys, in this video we will talk about the 3-phase inverter, which is a very important circuit and I didn't notice that it was on my channel, so I realized that it is time to do a simulation of the 3-phase inverter. Before starting, let me remind you a bit what is an inverter in just 3 or 4 words and what are the most common parameters used to simulate the inverter. So the inverter is a DC to AC converter. But the thing of the 3-phase inverter is that sometimes you have loads which are 3-phase brushed motor or 3-phase PMS motor, like this. And you can connect them with a delta or star connection. It's basically the same. So at the output in the 3-phase inverter, you have 3 phases, which are A, B, and C, and this is called the N, the neutral. And the line voltage is the difference between AB, AC, BC. So when you see VLL equal, it is the difference between VA minus VB. Or you can even study the voltage across one line, which is called VAN. So this is the terms that we will use and the most common employed. At the input side, you have the DC link capacitor. This is the DC link capacitor. Because I will simulate a VSI. The VSI is a voltage source inverter. There are also current source inverter, but I never studied them, honestly. In a voltage source inverter, you have to use a DC link capacitor. The capacitor, since it has an equation like I equal to C times the V over the T, the bigger the capacitor and the more current it is required to make a voltage change. So you can interpret a capacitor like this. It's like a spring in mechanics. And so in a voltage source inverter, you have to use a DC link capacitor, which is always a film capacitor, polypropane. So there are very specific high quality material for this capacitor. And so at the side you have current, which is ID, and a voltage, which is VD. The 3-phase inverter is basically we call phase two switches which are put like this in a leg. A 3-phase inverter, it has a configuration like this. Now, during the simulation, what are the parameters, the figure of merit of an inverter? So how can you say that an inverter is good? So what are the parameters? Well, aside from the efficiency of the inverter, which is of course the ratio between the output power and the input power, this can be of course a good measurement of the inverter. So efficiency is PO over Pin, of course. But aside from the efficiency, you have in the inverter, you have something very peculiar, which you don't have in the DC-DC converter. Let me remind you for a bit. In the DC-DC converters, 95% of the time, except the PFCs, in the DC-DC converter, you have just the switching frequency in the circuit, and in the spectra, you expect the component of the switching frequency, which is both in the input and both in the output, which have to be filtered, okay? But that's it. The inverter instead has something different. Since the load will be a motor, and the motor have a 6 Hz frequency up to 100 Hz, 200 Hz, but this is very exaggerated, because if you remember the characteristic of a motor, both DC but also brushless, for instance, they have they have a region like this. This is the speed, omega m, or let us say 60 Hz. If you use the flux weakening technique, you can increase the speed. This is the speed, but the torque will go down. Most of the motors follow this characteristic. And to reach this torque here, you have to go to the voltage, and you have to increase the voltage until you arrive at the nominal voltage, like 48 volts, 24 volts, and whatsoever. In this region, you generally keep the voltage constant, and you diminish the torque with the flux weakening. Most of the motors are like this. And so, the thing is, you have 60 Hz components, 100 Hz components, or even the line components. So this C can be even the line, the noisy line. Maybe you have a solar panel. The solar panel is DC. Then you have a DC-DC converter because you want to stabilize this, maybe a boost. And then you have an inverter, so a DC-AC. And this is fed to your house. And your house has 50 Hz, at least in Italy. In UK, 100 Hz, 120 Hz. No, I don't remember, but so you have the concept is you have two frequencies. First, it is the switching frequency of the inverter, and this can be this depends on the power application, but inverters have for motor application with 20 kilowatt, for instance, 20 kilowatt, but even 100 kilowatt. IGBTs are normally employed, and the switching frequency can be more or less 1 kilohertz. 1 kilohertz, 10 kilohertz also, 20 kilohertz if you want, okay? If you use SiC, with the SiC, you can realize an inverter with even 300 kilowatt, and the switching frequency can be also 100 kilohertz. But the SiC costs around $70 each, while the IGBT is basically zero, okay? €1. Nothing. Okay, that's the difference. These are employed for a custom application, but generally speaking, it is like this. If you want to realize a megawatt inverter, then use the Tristor or SSCR. So, and you want to know how much garbage, frequency garbage you get on the output, and so you need to study the harmonics. A factor is the TDH, which is the total harmonic distortion, and it is given by the sum of every harmonics aside from the first, so we indicate this of VO of n square over VO of 1. So basically it is the radical square of VO2 square, VO3 square, and so on. So you take the second harmonic, the third harmonic, and you divide it for the first harmonic, the fundamental harmonic. Then, of course, there is the modulation factor, the frequency modulation factor, which is MF, and it is the switching frequency of the fundamental frequency. The fundamental frequency is 50 Hz in my case, and the switching frequency will be 1 kHz in the circuit. And then there is also the modulation factor. The modulation factor, which is MA, it is the ratio between the control voltage, V control, peak to peak, over the triangular waveform. So to drive an inverter, you have different techniques. The first is the sine wave inverter. The second is the square wave inverter. And the third is third harmonic injection. So in the sine wave inverter, you have the sine wave, the triangular waveform. This switches at 1 kHz, and this at 50. And the result will be a varying, a non-constant duty cycle square wave, like this. The square wave inverter instead, it is the same with the triangular waveform, but the ratio. So here you have MA less than 1, 0.8, whatever, and then instead here you have MA larger than 1, and you have a sine wave which is like something like this, and the result will be the classical square wave. The third harmonic injection, instead, it is a technique in which you inject a sine wave like this, and with a demonstration, it is demonstrated that it will cancel the third harmonic. Then you have another famous technique, which is called the space vector PVM. Space vector PVM. The space vector PVM, it is basically a technique in which you switches the switch with a combination, with a particular combination, which ensure greater efficiency, no dead time, and no. So it is one of the best technique employed, the space vector PVM technique. So you can find online a table which you have Q1, Q2, Q3, and you have the space vector, which is made like 0, 1, 1, 1, 0, 0, 0, 1, 1. And so the concept here is that you can represent the space vector like this. There are 8 combinations, and two of this combination here, and they are called null vector state, and each 0 and 1 represent the fact that the switch can be open or closed. So 0 and 1, for instance, if we call the switches like this, let me change color. So this will be open, this will be closed, Q1 closed, and closed. So this is a combination. And with the space vector combination, you ensure greater efficiency and blah 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 blah. So this is one of the best employed techniques. In this video, I will use the same wave classical technique, and we will drive a PMS permanent magnet synchronous machine motor. So a classical AC motor. To make things clear, this is different from the DC brushless, because the permanent magnet synchronous machine motor needs an AC current, okay, and it develops an AC back MF. Instead, the DC brushless, there are different types of DC brushless, but one of the most used is the trapezoidal. And when you apply a pulse current like this, a stator current like this, you will develop a trapezoidal back EMF. This is one of the there are others of brushless, but this is one of the most employed which I used. So we will use this in my video. Then you can also import LTSPICE model for the DC brushless, and you will see that you have a trapezoidal square wave inverter, trapezoidal waveform. So the waveform that we are expecting now are something like this. This is the triangular waveform, okay, which I told you before. And then we have to make the control voltages, which are 120 degrees in phase with each other. So this is the first phase, then we have the second phase, like this, and the third phase is the other. So, to make you understand again, VAN is the voltage between between here and at the end of the motor here, okay? And this is like this. So, as the sine value increases, the duty cycle increases as well. If the sine value is low, the duty cycle is larger, as you expect. So, as you can see here, you have the minimum point of the sine wave, and you have a very, very low duty cycle. The same for B, and VAN minus VB of N is the line voltage. The line voltage, and if you perform a moving average algorithm, you will see that this is the fundamental line-to-line voltage one. So I think that you have all the bases now, and let's jump on LTSPICE, and let's see how we can simulate it. So the first thing that you want to know is to declare the variables. So dot param, we need the fundamental frequency f1, which is 50 Hz. Then we have dot param the switching frequency, which for now it is 1 kHz. And then we have the modulation, the triangular waveform. Let's v3. Let us put it to 1, and then we have the modulation factor MA 0.95. And of course, the control voltage of the sine, so it will be 0.5 times MA times V3. Maybe you didn't catch this parameter here, but basically from the modulation from the amplitude modulation factor definition, which is here, if you you can study the sine voltage V control, which is equal to V triangular times MA, and based on the region, you will have also a graph which is very famous, I think, which here you have the MA, and here you have different values. So when you increase MA to the respect to the control voltage, when MA is equal to 1, in the sine wave inverter you have 0.883. Then if you wanted the square wave modulation, I'm terrible, until it goes like this. So when MA is like, I don't know, 3, 4, there is no more dependence on the output voltage, and you have a value which is 1.113. You can find this demonstration on the book, but this is one of the most curve, and this is called the linear region, this is called the overmodulated region, and this is the square wave region. And so we will declare it like this. Now let's generate the control voltages. So let us use let us call this V control A, and come on, okay. So the first will be a sine wave with an offset which is V3 over 2, an amplitude which is V control, a frequency which has to be exactly the same as the line, so f1, and the phase degree, I will put it 0 for now. So then we have V control A, V control B, and V control C. Now, just put B here, and let us put a phase degree of 120, and V control C with a phase shift of minus 120, or 240, but it's this minus 220, it is better. Now we have to make the condition for the Smith trigger. You can use the Smith trigger or simply a behavioral voltage. We will do like this. So let us put a behavioral voltage B1, BV, and we will say that when the sine here is greater than the triangular waveform, so when the sine is greater than the triangular waveform, trigger to 1, like this. So the condition becomes when V3, when V control is greater than V3, 1, 0. So, and we will insert this. So when V3, when V control V of V control A This is too complex. Let me cancel the L. CTR is preferable. So when V of if V of V CTR of A is greater or equal than the triangular waveform V3, go to 1, like this. Now, since the switch is high side, you need the gain like this. Let me put it here. We must be careful here because we can't waste any space. This ground here has to be connected to the same ground of the guy, of the BV generator. The gain will be 1. And now we will connect it to the switch of the first phase. For now, I will use an ideal switch because I think that the simulation will be quite heavy. So I don't want to make you waste any time, and this will be my block for the switch. Just like that. And now when we declare the model of the switch, dot model switch around the milli of resistance to 10 MHz and threshold voltage to 0.1. And now it is it's finished because you basically have just to copy and paste. If you arrived to this part of the video is finished because now you have just to copy and paste everything and you have done. So this will be leg A, and instead putting greater or equal, you just put less than. Now if you draw, you can draw a rectangle, and all of this is the leg A. As such, this will be voltage A. And this will be the ground. So the only thing left to do is to copy and paste this for each leg. Okay? And then you substitute it with B and C, and you get done. Okay, I think that there is no need to show this on the... So when control B, here you put B. So I think that there is no need to show this because it's literally the same for each one. So you can't get it wrong. Just A, B, and C. This is B, and this is C. So, since it is useless, just don't show it. Each of the leg is then connected to the DC voltage, which will put it here. The DC voltage is quite high in my example, and let's put 344 volts. Now you need actually the motor, and to do this, we have to remember how the PMS motor is done. The permanent magnet synchronous machine motor can be in a can be represented with an inductance, a resistor, and the back EMF, which is a sinusoidal, which is a sinusoidal waveform. So to each leg, we will now have the motor. I think that we can. Leg A, leg B, and leg C. So now you can understand why it is called 3-phase inverter. You have 3 phases. Each of these legs is a phase. So let's use the motor. 3-phase inverter for PMS motor. Ta-da! And you have also the space for the title. So let's put the motor. The first back EMF, the resistor, and inductance. A value of the inductance can be even 10 millihenry because we are simulating a very big motor and a resistor of 2. Then, since we will attach this to the A voltage, we will have a DC offset of 0 and an amplitude of, I don't know, 75 volts, and a frequency of the fundamental frequency F1. Because this is the frequency of the motor. And as I said before, this is the second frequency in the system, which will cause a lot of noise. And 0 phase and 0 degree phase. This is connected to A. And we will perform a delta connection. So let us put everything like this. A, B, and C. Now remember that these have to be, this has 120 shift phase, and this has minus 120. So you have your motor. Again, this is useless, so let me do not let me show this on the schematic. Let me do something like this and save space. Now we need to visualize also the frequencies, and to do that we can use the statement.for, but I can show you that later. It is not so hard. And now the only thing left to do is to run the simulation. And let's see what happens. So let's run for 100 milliseconds. Okay, 3. Okay. I've done everything, but what I missed was the triangular waveform. So I'm very, very dumb. I forgot the triangular waveform. So let's look at the triangular waveform as a pulse. The initial voltage is 0, beyond is 1, delay is 0, and the rise time is 1 over 2 times switching frequency. These values are not random, okay? And none T-on 0. And the period is 1 over Fs. This is not a random statement. If you take paint, you will understand. Now, this is a triangular waveform. This is the period, which is Ts. and so TS it is equal to 1 over the switching frequency. And if you wanted a symmetrical waveform, this will be 1 over 2 Fs, and the other will be the same, 1 over 2 Fs. This time in which it is on, for SPICE it is something like this. If you put it to 0, it will be like this. And so let's run the simulation, let's run it, and okay, I forgot to put the parentheses in the correct order. My bad. Even here. Okay, so here you have the same voltage. Okay, you have the same voltage here. The three same voltages which are correctly in a phase shift of 120 degrees. And then you have, and this is enough. Let's see for one phase what is going on. So this is the control voltage. This is the triangular. This is the BV. So as you can see, you have a non-linear. You have a non-linear duty cycle here. It is higher, which when the sign is higher, and this is the current of the switch, and this is the current of your motor. So aside from the transient, you see that there is a little bit of ripple, and this ripple is given by the fact that the switching frequency is not so high. So if you accidentally increase the switching frequency to 10 kilohertz, which it is reachable, it can be reached by the IGBT, you can see that it has improved. The ripple has improved a lot, and so the ripple depends both on the switching frequency. Let me put again to 1 kilohertz, but also on the modulation factor. If you decrease the modulation factor, MA, to 0.7, this will increase because you are not, the ripple will increase, as you can see, because you are not exploiting all the sine wave, which is given here. So you're not exploiting all the triangular waveform, which is given here, and so you won't have an accurate representation of your Kyler. And so MA we will put to 0.95. If you put MA to 10, for instance, what's gonna happen is that you have an overmodulated voltage, and the result will be just a square wave, like this. And this is not exactly a square wave inverter, but it is the principle of the square inverter. You over-exaggerate your sine waveform with respect to your triangular waveform, and you will have a driving done with the square wave. So the result will be very peculiar, because you have a ripple on the maximum value of the sine, which is to be expected because the sine wave is saturating, but you have less ripple on the ongoing waveform. So the waveform here is quite clean, as you can see, but this is not so beautiful, and the square waveform is not one of the most employed techniques. So let me put again MA equal to 0.95. Now, if I put the screen here and run again a simulation, so you see that this technique has less ripple, but it has a distorted waveform around here and also around here. So there you have a distortion around the peaks. And another thing interesting to see in the square wave inverter is let's skip the transient first of all. Let's skip the first 20 milli. As you can see, the simulation is very fast. Is to see the spectra of this guy here. So let me view the spectra with the FFT, and we will choose this current which is highlighted. Okay. Now what you can see here, is to you can see in both linear but or in decibel. If you put it in linear, maybe it is more clear. For me, it is more clear because here you have the fundamental component at 50 Hz. So let's enlighten that. You can enlighten this with F4. Sorry, F4. So at 50 Hz, you have the most carrying components. Then, as you can see here, we have the harmonics. And around the switching frequency, which is 1 kHz, in the left and right side, you have the two, you have the first harmonic, basically. Then, this will be the second harmonic at the 2 kHz, as you can see. And this is when this will be the third, this will be the fourth, the fifth, and you got the picture. So this is the spectra of the inverter. You have the first contribution at a lesser frequency and the other contribution at the switching frequency. The only thing left to do is to actually study the parameter which I told you at the beginning, which is this. This is the total harmonic distortion factor, and this is calculated automatically by LTSPICE with a command which is called .4. And if you press F1, you can open the guide with F1, and if you search for, it will give you an example of a syntax, an example of how to use the for statement. You see the total harmonic distortion, which is nothing because you don't have ripple in this case. Okay, now it is correct. So if I put again 1 kHz and you run the simulation, you go to edit, error log, okay, 5%. So it is acceptable. Let us use all the harmonics until the 10th. 5%. It is acceptable. If I decrease drastically the switching frequency, you can imagine that it will increase. The harmonic distortion will, of course, increase to 12%. So, well, guys, I think that I showed you everything about the 3-phase inverter. And I don't think that this is, for a basic video, I think that this is enough. The only thing left to do is to show you the line-to-line voltage, VHB, which is something like this. And it is the same of the textbook which I used. The other are of course in line, are of course in phase, switching frequency 1 kHz, and I think that I can close the video. Thank you guys for seeing this video, and see you in the next one.